Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book Algebra in Action, a course in groups, rings, and fields. The subject of this lecture is cancellation in groups, and among other things, we will prove that finite semigroup together with cancellations are the same as a finite group. We will also look at the definition of a group in a little bit more detail and see if there's some redundancies. The group is a non-empty set together with one binary operation, which is closed. It's associative. There's an identity and there are inverses. I've had other videos where we have gone through the definition of a group and many examples. In this lecture, we will look at some patterns in the multiplication table. We will notice that the group multiplication table is a land square. That means that there's no repeats in any row or any column. And that is the same as saying that we have a cancellation law, that if you have ax equals ay, we can cancel the a's on the left or on the right. We will also prove that identity and inverses are unique. That's not a part of the definition, but we will prove that they're always unique. We will also prove that in the definition of a group, we didn't really have to have a full-fledged identity and full-fledged inverses. If you had left identity and left inverses, that would have sufficed. Also, we will prove that a finite semigroup with cancellations is a finite group, but I will tell you what a semigroup is later. We'll start with patterns in multiplication table of groups. Whenever we want to think about something, it's good to start with some examples. Look at some of the groups that we know and see what kinds of things we see, and then we will prove them in general, not really basing them on the examples. But examples are a good way to start. And I will start with the group D8, dihedral group of order 8, the symmetries of a square. I have a whole video on D8 with a lot of detail, but all you need to know here is that D8 is a group that's generated by two elements, A and B. A is the 90-degree rotation, and B is a horizontal reflection about an axis that goes through the middle horizontally. We have the relations that a to the fourth is e. If you rotate 4 times, you get back where you started. B squared is e. If you reflect twice, you're back where you started. And BA is the same as a cubed B. For any group, if you have the generators and if you have the relations, then you can write down a multiplication table. On the rows, I've written down all the elements of the group. This group has 8 elements: E, A squared, A cubed, B, AB, A squared, B, and A cubed B. And I've written the same things as headings for the columns. The actual multiplication table is this part in the middle. For example, A times A squared is A cubed. B times B is E, but B times A is A cubed B. And AB times A is B, and so forth. So this is a multiplication table. If you're not familiar with multiplication tables or don't know what I'm talking about, then you definitely should be watching the video on D8 before you go any further. In some sense, all the information about a group, everything we want to know about the group is already in this multiplication table because a group is a set together with one operation. In some sense, all group theory is finding patterns in the multiplication table. Now, this tends not to be a very productive point of view to focus on the multiplication table. The right point of view is to think about structures and substructures and how they relate information. That will be productive. But at the beginning, since we don't have any other tools, we start with the multiplication table and see what patterns we see. One pattern that we do see is that there's no repeats in any row or in a column. In every row and every column, every element appears exactly once. Whenever you see a pattern in a group, you should always look at a number of different examples. And our go-to examples, dihedral group of order 8, the abelian groups Z mod and Z, as well as the symmetric groups. So matrix groups are also good, but they're usually a little bit harder to write down and think about, at least at the first pass. The more sophisticated look at group theory will tell you actually the matrix group is the best kind of examples to look at. If you look at Z mod 4Z, for example, remind you that 0, 1, 2, and 3 are the elements, and the operation is addition modulo 4. If we write that addition table, we see that in every row and every column, every element appears exactly once. Finally, S3, this is a group of order 6. It's one-to-one onto functions from 1, 2, 3 to 1, 2, 3, the set of all permutations of 3 things written in cycle notation. So parentheses 1, 2, 3 means 1 goes to 2, 2 goes to 3, 3 goes back to 1. E is identity, nothing is moving. 1, 2 means you switch the place of 1 and 2 and keep 3 fixed. We have 6 permutations. And if you write down the multiplication table, you will also see that there is no repeats in any row or any column. To say that there's no repeats in a row labeled A, what does that mean? That means that if X and Y are 2 different columns, then X, which is the entry in row A, column X, is going to be different than AY, which is the entry in row A, column Y. The counterpositive is that if AX equals AY, then X equals Y, which brings us to cancellation. So to say that there's no repeats in every row is the same as saying that you can cancel on the left. To say that there's no repeats on any column, similarly, is the same that you can cancel on the right, the cancellation properties. If you have a group, then I want to prove that AB equals AC implies that B equals C. You can cancel on the left, and you can also cancel on the right. BA equals CA implies that B equals C. This is a very straightforward proof. I suggest that you stop the video and prove it yourself, and then skip the proof. But here it is. If AB equals AC, how am I going to get B equals C? In high school algebra, you would say, well, just cross out the A's. We don't have a crossing out operation. In fact, we're trying to prove that we do. That if two things are on the leftmost part of an equation, we can cross them out. But the way to do that is multiply both sides of this by A inverse. We'll say A inverse times AB is the same as A inverse times AC. How do I know that? Well, AB is the same as AC. So A inverse times AB better be the same as A inverse times AC. But now you can switch around the parentheses. Why? Because one of the properties of a group operation is that it's associative. And then A inverse A is identity, and we have identity times B is identity times C, and identity times something is itself, so B equals C. In fact, we used all four axioms of group theory to show that you can cancel on the left, and canceling on the right is the same, except you have to multiply both sides by A inverse on the right. Let's quickly also prove some other elementary properties of groups. Say G is a group, then we want to know that the identity element is unique. As a part of saying that something is a group, we already know that it has an identity element, but the definition didn't say that it has to be just one thing that acts like identity. Maybe you walk in some group and there are several elements that would like to play the role of identity. But we are saying that's not the case. Every group has just one identity. We also want to say that inverses are unique. Again, as a part of our definition, every element has an inverse. But what we did not say is that that inverse got to be just one element. In fact, when we talk about the inverse, we are assuming that the inverse is unique. Before proving this, all we know is that every element has an inverse, maybe more than one. The third elementary thing is to say that A inverse inverse is A. The inverse of A inverse is A. And the last thing is that if A and B are elements of G, then AB inverse is the same as B inverse A inverse. Order matters because groups are not commutative, so it's not A inverse B inverse. This is an example of a shoes and socks theorem. If you put on your socks and then shoes, but then you want to take them off, you have to take off your shoes first, then socks. And this is the same thing. AB is two operations in an order. If you do AB and then you want to undo it, you have to undo B first and then A. Let's prove this. Let's prove that the identity is unique in a group. How do we prove that? We assume that we have two identities. Walked into this group and we asked, who's the identity? Both E and E prime got up and said, I'm the identity. And we want to settle that dispute. Could they both be the identities for the group or not? What we're going to do is we'll multiply E times E prime. When you multiply E times E prime, E will say, well, I'm the identity. Therefore, when you multiply me by E prime, you should get E prime. But then E prime will say, wait a second, I'm the identity. So if you multiply E by E prime, you should get the other guy, E. Therefore, E is equal to E prime. If E and E prime both have the identity property, then they must be equal. That's the proof that the identity is unique. Now let's prove the inverses are unique. Assume B and C again are inverses of A. A is this element. We ask, who's your inverse? Both B and C are saying that they're the inverse of A. Could that be true? I'm not doing this proof by contradiction in the sense that I'm not assuming that B and C are different and then getting a contradiction, but I'm going to assume B and C are inverses of A, reserving judgment on whether or not B and C are two different elements or the same element, and then we'll prove that they're really the same. I thought I heard two different people saying that they're the inverse of A. They were not. They were the same guy. What we know is that BA equals E equals CA because B is the inverse of A and C is the inverse of A. If you have BA equals CA, we just proved that we have cancellation. And by cancellation, we can cancel A and we get that B equals C. We don't actually need both cancellations to get this fact. We just needed left or right a cancellation and we would have got that B equals C. The next thing was that A inverse inverse is A. What does that mean? That means the inverse of A inverse is A. If someone says, I'm the inverse of something, to check that, you just multiply it to see if you get identity or not. Here, A is suggesting that the inverse of A inverse. So let's multiply them and see what we get. If you take A and multiply it by A inverse, you get identity. That says A inverse is the inverse of A, but it also says that A is the inverse of A inverse. How do I prove that AB inverse is B inverse A inverse? Again, this B inverse A inverse is walking to the drawer and making a claim. Its claim, the claim of B inverse A inverse is that I am the inverse of AB. There's AB, I'm its inverse. That's why I'm AB inverse. Therefore, to check that, you take the claimant, B inverse A inverse, and multiply it by AB, see if you get identity or not. Multiply AB times B inverse A inverse using associativity. B times B inverse is identity right in the middle. A times identity is A times A inverse is E. So you get identity. And if you multiply the other way, same thing happens. The A inverse and A in the middle cancel, give you E, and then E times B is B, and you get E again. And so AB and B inverse A inverse are inverses of each other, which means that AB inverse is B inverse A inverse. I want to say a little bit more about E, the identity. Let's say G is a general group and E is the identity of that group. We just proved that E is unique. I want to point out that also follows from the cancellation laws. And that's because if there was more than one E, then in the multiplication table, the rows associated with those two E's would be identical. And therefore, in every column, there would be a repeat, but we proved that there are no repeats. What does it take to check that something is identity? The definition of identity is that E is the identity if when you multiply it by every element, XE, EX, you get X back. And that has to be true for every element of the group G. If you happen to be inside a group, if you know that G is a group and you have this claimant, Z is walking to you and saying, I'm the identity, and you want to check that, a priori from the definition, you might think, I've got to take Z and multiply it by every element of the group both ways and see if it changes anything or not. However, this is not necessary. If you are already inside a group, all you have to do is check one element. Take that Z that is claiming to be the identity, multiply it by 1x, one element of the group, and see if it acts like identity. If it does, then it is actually the identity. And that follows from the cancellation law. Why? If Zx equals X, then Zx equals EX. E is the identity of the group. Maybe Z is the identity, maybe it's not. We're reserving judgment about that. But E is the identity, and we have Zx equals EX. And then we can cancel on the right the X's, and we get Z equals E. We could have done the same thing if we had XZ equals X. We would have also got that Z is the identity. If you're walking inside a group, you're checking inside an actual known group, and if you have some element that is claiming to be identity, all you have to do is do one multiplication, and you will know if you've got identity or not. This does not work if you don't know that you're in the group. If you're trying to prove that something is a group and you're trying to look for identity, it's not enough to multiply two elements and say, look, this guy looks like an identity. It may not be the identity, because it might be that when you multiply by other things, it doesn't work. But inside a known group, checking for identity is very straightforward. We want to spend a little bit of time thinking about the definition of a group. In fact, the first thing I want to prove is that there's some redundancy in the way we define a group, in the sense that we don't need the full force of everything. We could have made a definition that was slightly weaker. Let's say that you've got an operation on a set and assume the following things. First of all, this non-empty set is closed under the operation. I also want associativity. So closure and associativity. Usually for a group, I would want identity and inverses, but I'm not going to say that. I'm going to say something weaker. Assume that G has a left identity. What do I mean by that? I mean that there's some E that E times every element is the same, but I don't know about it being a right identity. Just assuming that it has a left identity. I also assume that it only has left inverses. What does that mean? That means that if you give me an A and G, there's some other element that I'm going to denote again by A inverse, but all I know is that A inverse multiplied by A gives you that left identity. So I'm not assuming that I have an identity. I'm not assuming I have inverses. I'm just assuming left identity and left inverses. This is weaker than the definition of a group, yet I'm going to prove that G is a group. And what do I mean by G is a group? I mean that the left identity is actually also a right identity, that left inverse is also right inverse, and so forth. This does not say that if something is a left identity is automatically a right identity. It says if a set has closure associativity, the left identity and left inverses, then those are identity and inverses. Let's now prove this. The first thing that I want to claim is that because we have left inverses and a left identity, we have left cancellation. And the proof is the same proof as the cancellation. If you go back to that proof, left cancellation follows from left identity and left inverses. The second claim is that E is not just a left identity, it's also a right identity. But that I have to prove. I take an A and G. I know EA is A, but now I want to prove that A times E is A. How am I going to do that? I do know that there's a left inverse. I can't just on its own
alone prove that the left identity is right identity. I need to know that there's also left inverses. So there's a left inverse in A inverse, and so I know that A inverse times A is E. I don't know A times A inverse is E, but A inverse times A is E. Instead of E, I can write E times E. That's correct because the left E is a left identity, and so that works. And instead of that first E, I'm going to write A inverse A again. I have that A inverse A equals A inverse A E, and I can cancel the A inverses on the left because I have left cancellation. That gives me A equals AE, and that's what I wanted. I just proved that E is also the right identity. If you have A and G, we know that we have this left inverse, which we call the A inverse, but I want to show that A inverse is also the right inverse. Look at A inverse times E for a second. That's A inverse because E now is the right identity, so I know that's A inverse. But E is also the left identity, so this is the same as E A inverse. And instead of E, I can write A inverse A because A inverse is the left inverse. So I have A inverse A times A inverse. And what I'm going to do is switch parentheses because of associative. And then I have A inverse times E equals A inverse times A inverse. But now I can use left cancellation again and cancel the A inverse, and I get E equals A inverse, and I'm done because I've proved that A inverse is also the right inverse. And therefore, the group has an actual identity and an actual inverse for every element, and therefore it's a group. We're done. You might get the impression from this whole lecture that group theory is a lot about this kinds of calculations. This kind of calculation sometimes happens, but very rarely actually. Don't get the impression that this is what we're going to be doing the whole course. Not so.
I want to tell you some vocabulary, Latin squared semigroups, and the relationship with groups. If you have n symbols, and if you make an n by n array, if you fill the entries with those symbols, the array is called the Latin square if there's no repeats in any rows or columns. Now, cancellation property of groups told us that multiplication table of a finite group is a Latin square because there's no repeats in any rows and columns. If S is a non-empty set and if you have an operation, if you know that S with that operation is closed and associative, and that's all you know, then this is called a semigroup. A semigroup is not quite a group because it doesn't have an identity or inverses, or you don't know if it does or not. A semigroup is when all you know is that you have closure and associativity. A monoid is a semigroup with identity, and a group is a monoid with inverses. Monoid has everything other than inverses, and semigroup only has closure and associativity. The next theorem that we want to prove is that if you have a finite semigroup with cancellation, if you have a finite semigroup and you know that you can cancel, then you have a group. In other words, we want to prove that if you have a non-empty set, it's a finite group if and only if it's a finite semigroup with cancellation properties. Another way of saying the same thing is that a Latin squared with associativity is a group. A Latin square already has the cancellation properties because there's no repeats in rows and columns, and it's closed. You have closure and cancellation, and if you add associativity to it, then you have a semigroup with cancellation, and therefore that's also a group. Let G be a non-empty set with an operation. Assume that G is finite, so there's finite number of elements in G, and we have closure and associativity. And assume that you have cancellation on the left and cancellation on the right. So you have left cancellation and right cancellation. Then G is a group. If you have a group, then you have cancellation. But if you have cancellation, you have a group. Cancellation is equivalent to having an identity and having inverses. We have to show that this set together with this operation has an identity and has inverses. Let's prove that. The key thing here is the finiteness. And this argument actually is worth knowing about because it's one that might be useful in other places as well. The set supposedly has a finite number of elements, so maybe it has n elements, and I'm naming them A1 through AN. So that's what G is. I need to find you an identity and an inverse. What am I going to do? How am I going to find one? I'm going to start with one fixed element. Because it's not empty, there's at least one element. Pick one element. If I'm lucky, that element is the identity, but most likely it's not. I just picked just one element, B. We'll take B and multiply it by every element in G. In other words, I'm looking at the row of B in the multiplication table. That means I'm looking at BA1, BA2, BA3 to BAN. And I'm going to ask, could any of these be the same? And the answer is no. If two of them were the same, if BAI was the same as BAJ, then I could cancel on the left and I would get AI is AJ. So if AI and AJ are different, BAI and J will be different also, which means that that set of elements has n elements. So there's no repeats in it and there are n elements. And all of them are in G. So this must be exactly G.
This does not mean that A1 is BA1 and A2 is BA2. No, these might have been permuted. But when you multiply by B, just like in a multiplication table of a group, you don't get them in the same order, but you get them in some other order. But that means that B is among these. So B is equal to B times AK, and AK is going to be our candidate for identity. Do we know that it's the identity? No, we don't. In fact, the only thing we know is that AK is the right identity, not even for all of G, but just for B. So B times AK is B is the only thing we know, but we now have to bootstrap that to make that AK is actually the right identity. We start by looking at B times B. And instead of the first B, I'm going to write BAK because B is BAK. Then I'm going to use associativity and write that as B times AKB. Cancel the B's, the blue B's on the left, and you get that B is AKB. I still don't know that AK is identity. It's just the identity for B, both left and right, but not necessary for other elements. That's the next thing we have to do. So far, we have that this group has two manifestations. You can write it as A1 through AN or BA1 through BA. Now we want to show that AK is a left identity for all of G. We pick C and we want to show that AKC is C. That's what it would mean to say AK is a left identity. G we know is BA1, BA2 through BAN. That's one way of writing the elements of G. So C must be among them. So C is BAJ for some J between 1 and N. Now let's look at AKC. We want to show that AK is a left identity, and that's why we want to look at AKC. C is an arbitrary element. If AKC is C, then AK is the left identity for all of G. Instead of C, I'm going to put BAJ. Use associativity. And remember, AKB is B because AK is the left identity for B. In fact, is the identity for B. So I get BAJ. But BAJ is C. So I got AKC equals C. And so AK is the left identity for all of G. Maybe I should show that AK is the right identity. I don't need that because of what we proved before. I'm going to now go for inverses. So let C be in G, and I want to find a left inverse for C. I'm going to look at A1 through AN, which was the group G, and multiply all of them by C. So this is the column associated with C in the multiplication table for G. Again, because of right cancellation, this is going to be G. And this is actually the only place I use right cancellation, because if AIC is AJC, you can cancel C's on the right and I will be the same as AJ. And because that's G, then that means that one of these, maybe ALC, is AK. That means that AL is a left inverse for C. We have a left identity for all of G, and every element has a left inverse. We have closure, associativity, left identity, and left inverses. And earlier we proved that that's actually all you need for a group. You don't need to prove right inverses and right identity, and therefore G is a group by what we proved. I'm almost done. I'm just going to give you a remark that I'm definitely not going to prove. This is a cute little thing, a little puzzle that logicians are actually interested in. Two mathematicians, Higman and Neumann, in the 1950s showed the following. They showed that if you have a non-empty set and you have binary operations called slash, and you know that for all elements X, Y, and Z in your set, you have the following weird condition, then G is a group. Not group with this operation, but with some other operation that you define in terms of this slash. But the point is that G will be a group. And the point of this is to show that you could define groups using just one axiom.
This is the end of this lecture. Like my video if you liked it, and subscribe to my channel if you want to be subject to math videos in your feed, and keep hydrated at all times. See you in the next lecture.